Nobody on the road, nobody on the beach. I feel it in the air, the summer's out of reach. Empty lake, empty streets, the sun goes down. I'm driving by your house, oh, I know you're not home, and I can see you. Your brown skin shining in the sun. You got your hair combed back and your sunglasses on, baby. I can tell you my love for you will still be strong after the boys of summer have gone. Hey everybody, welcome to this week's edition of Video Notes from Mr. Flugum's AP Chemistry class. That's right, folks. This one's for AP Chem. And we are going to be talking about light and quantum theory. This is a little bit of review. Most of it you covered last year in Chem, but it's stuff that we need to know and be able to use. So let's go ahead and get started. So hey, one thing I want to do before we really dig into the deep stuff is this, to talk about components or parts of a wave. So one part that you need to be familiar with is the wavelength, which is represented by this symbol here, which is called a lambda symbol. It's a Greek letter, okay? And basically, when you see that, that means wavelength. Okay, wavelength is a distance. So it's a distance between two similar points on a wave. It can be crest to crest, like it is shown here, trough to trough, or any two similar points on a wave. Most of the time in this presentation, you'll see it measured in nanometers, which is 10 to the negative ninth, right? Which is nano, 10 to the negative ninth meters. The other component of a wave that you need to be familiar with is the frequency. Okay, so frequency of a number of times a wave repeats itself per second, or you could basically say this is wavelengths per second. Okay, and it's represented by the symbol V. Okay, so with those two pieces of information in mind, let's look at this formula right here, which is kind of an important formula when it comes to light. All right, so we have the speed of light, which is c, which is more or less constant at 3 times 10 to the 8th meters per second, right? Then we have the wavelength here, and notice that it's in meters. So a lot of times you'll get problems that will give you the wavelength in nanometers. We of course need to change that into meters, and don't forget that nano, it means 10 to the negative ninth, right, which is a billionth. And we have the frequency here, which is in hertz, right, which is seconds per seconds, right? So here we want to find the frequency of some green light, and we are given, of course, the wavelength here. And we just want to use that equation that I talked about on the last page, right? Speed of light is equal to wavelength times frequency. Of course, our speed of light is 3 times 10 to the 8th, right? And our frequency is in nanometers. So we have to make that transition from nano into meters, because our speed, of course, is in meters per second. So I changed this wavelength into meters, and when I did that, I got 5.45 times 10 to the negative 7th. Okay, and of course that's times our frequency. Okay, so we just got to do a little math here. Divide by 5.45 times 10 to the negative 7th. That, of course, is in meters. Sorry for not putting the units. And we get a little bit of magical math here. Units cancel out. Okay, and I got this. I got 5.50 times 10 to the 14th power. That is hertz. Okay, or you could say per second, right? That is our answer right there for the frequency of that wave. So this here is our continuous spectrum of light. These are all of the electromagnetic waves within the spectrum, and you can see it goes from extremely small gamma rays down here, which have wavelengths in the fractions of nanometers, right? 10 to the negative second nanometers, all the way up to radio waves, which have wavelengths which are relatively long. And in fact, you could even measure some of them in kilometers. Right here in the middle is visible light. This is light that we can detect with our eye and see. So all of this light, all of these electromagnetic waves, the speed can be calculated using the formula that we had on the last page, right? C equals wavelength times frequency. So here's where the hard rubber meets the road, folks. Quantum theory and Max Planck. We'll also get this guy involved too, Albert Einstein, when this is all said and done. But basically, Max Planck was a physicist who lived around the year 1900, and he had this hypothesis that instead of energy being a continuous kind of radiation, it actually is emitted in what are called discrete units. He called them quanta. We assume that energy is a constant stream like this. Instead, experimentation as well as theory has shown that it is actually released in discrete units, right? So it's either a full unit or no unit at all, okay? Full quanta or not at all. So as energy goes up and intensity increases, quanta goes up in a stair-step-like fashion. So soon after Planck's work, Einstein was on the scene. Really, they were contemporaries of each other. Max Planck and Einstein knew each other, worked together, disagreed, but sometimes agreed. So, you know, it's just a story of science, okay? Now, Einstein needed to explain this thing. He needed to explain something called the photoelectric effect. Now, scientists had known for a long time if you shine certain frequencies of light onto metals, those metals would give off electrons, kind of like solar energy, right? Well, they didn't know why it was only certain frequencies of light. It didn't matter how intense the light was. What mattered was the frequency. So we needed to be able to explain this. So Einstein, that's a Y by the way, so Einstein came up with this idea of photons. So photons are particles of light. And those photons would have energy that is equivalent or related to quanta, right? So their frequency and Planck's constant, which we'll get to in a second, would tell us the energy of a photon, okay? So if the frequency is a certain amount, then the photon doesn't have enough energy to eject an electron from an atom. However, if there's enough frequency and enough energy, okay, then this can cause electrons to gain enough energy when they absorb a photon, right, and actually be kicked off or ejected from the atom. So that brings us to this idea of energy per quantum. How much are those stair steps that are given off? And that's related to two things. We have Planck's constant, which is kind of how many joule seconds there are, right? And the frequency of the wave or the photon. All right, so let's talk about this real quick, right? How do we use this equation? So we want to know this: how much energy is transferred by a wave that has a frequency of 5.5 times 10 to the 14th hertz. Okay, well, we're going to use our E equals HV equation, right? Whoops, sorry about that. Get the right thing here. So here we want to find our energy, which of course will be in joules, right? And that is just Planck's constant, right? 6.63. You may have heard it as 6.626. It just depends on how many sig figs you want to use, right? Times 10 to the negative 34th joule seconds. Okay, and we're going to multiply that times our frequency here, right? 5.50 times 10 to the 14th. Okay, hertz. Now once I do that math, okay, I end up with this, right? And I'm going to round it to sig figs. Okay, my E is equal to 3.65, right, times 10 to the negative 19th joules. That's how much energy is transferred by photons with that frequency. I have one down here at the bottom for you to try before we leave. It says how much energy, right, is in a wave that has a wavelength of 440 nanometers. Now, in order to do this, you have to go back and use the C equals lambda times frequency one in order to find, the frequency, and then you can use this equation right here to find how much energy. So it takes 2 steps to do that one, right? Well, thanks for tuning in, folks. I hope you have a great day, and I will see you in class tomorrow. Bye-bye.